Ladies and gentlemen, please welcome Herb Sutter.
Hello, thank you very much for coming. Thank you for coming, even in a session scheduled at the lunch hour. I'm told you will have lunch available after the session ends, and I hope to make it worth your while. So over the last couple of days here at Build, you've heard a number of talks that have included C++, some specifically about new features that are related to Visual C++ in the IDE, IntelliSense, debugger, and libraries. But we had quite a bit to tell you about one particular feature, so we reserved this session to talk about just one thing primarily, and that is Visual C++ and conformance to the ISO C++ standard. And so over the next bit of the session, I'm going to do something we promised we would do. We said we've been working on it, so we've been doing that, and we'll share an update as to how we're doing, what you can expect, and about when. But we also said we'd tell you more when we know. Well, we know a bit more now, and so we know enough to give you something that we've never actually laid out before. And so for the first time, we're going to lay out an end-to-end roadmap to achieve in Visual C++ full conformance to ISO standardization. How many of you are interested in that? And when I say full conformance, I'll define what I mean by that at the end of the talk. Darn, I was really trying hard to freak out about half the audience by saying that. Now, so by full conformance, I actually don't mean exactly what you probably think, but don't worry, it's a happy surprise. But first, let's talk about C++ in the broad world and in ISO standardization. And I'll give you a quick update of things that have been happening recently in C++ internationally in standardization. In the C++ Standards Committee, we've been growing, and we've been adding a number of study groups and subgroups. So at the bottom, this is an update of a slide I showed you last year. Starting in 2012, we started creating these study groups, which are focused on specific topic areas, and we're now up to 16 of them. And they're each working at their own speed in different areas, from file system and networking to numerics. We started one just on databases, on modules, things like that. Some of them are shorter items, some of them are long poll items, some of them are library features, some of them are language features. But one of the things that we've noticed is not only has that helped us organize our growing committee, because the industry is investing much more in standard C++, so our membership keeps going up and attendance at meetings. But it's also drawn in people who never were involved in C++ standardization before. So for example, we created a study group on a particular topic, say parallelism, or we created one on transactional memory. And for the first time, because there was a home for this work that would do its own work and have its own meetings between full standards meetings, suddenly we started seeing the top world-class experts in those domains who cared about C++, but not enough to come to a general ISO meeting, participating directly in these efforts. That really helps the workload. Having many hands makes light work, but it's also quality input by top experts in the field. So we're very glad about that. One of the results that we've seen is that I showed this slide before, that our meeting attendance has been going up. There was a spike when we finished the C++ 11 standard, because everybody wants to be at the meeting where you vote out the new standard. I was there. You can see me in the picture. But even after that spike, we've noticed as the C++ 14 effort began that membership has increased. And an update to that is that we actually blew past recent memory highs of attendance in ISO C++. And thank you very much to the British Standards Institute and to ACU and several other hosts mentioned on isocpp.org for hosting us in Bristol 2 months ago, because we blew the doors off what they expected to get, and they graciously were able to accommodate a larger meeting significantly than planned. And we had a very productive meeting with 107 people voting, working around the clock, and actually voting out, this is the important milestone, the complete feature set for C++ 14, which is now in its primary international ballot as we speak. Most of the new features in the upcoming C++ 14 standard were added 2 months ago. There were a few that were voted in the meeting before or two, but most of them were voted on just 2 months ago. And going into that meeting, nobody knew which ones would be approved or in what form exactly. So now, for the first time, we know the shape of C++ 14, and over the next year, we'll be responding to national body comments, doing refinement, bug fixing, editing, but we know the feature set, and that is an important milestone. When we look at the history of standardization, we can see that things were pretty quiet as we worked on C++OX, which became C++11. But now, in just a few short years, we are on a more rapid cadence where we are delivering a standard that is not as big of extensions as C++11 was, but contains meaningful and important extensions that really complete C++11. And 3 technical specifications that are separate documents that are on track to be delivered at the same time. We hope to complete all those in the next year, which is a pretty good cadence. And also by decoupling some of those items, such as file system, they can work at their own pace. When you have a monolithic standard, you try to jam everything into one time on target release. This lets us release things more fluidly and hopefully more often. And so this C++14 wave is something that we're very happy to have been able to achieve, and we're looking forward very much to that. When you look at C++14, it's really important because, as Bjarne and others have said, C++14 really completes C++11. It adds a few features that make the C++11 features more general and regular. They work everywhere. And because of that, when it comes to conformance, I'm pleased to say that as a team, the Visual C++ team, when we look at ISO C++ conformance, our goal is not to conform to C++11 only, but to conform to C++14. And let me be very clear what I mean by that, because that could sound scary. It could sound like, oh, look, an excuse not to do C++11. No. But rather what it means is because C++14, which is really C++11.1, but 14 is the year it came out, it really completes the story. And so we're going to look at all the remaining feature work for the C++14 and 11 standards as one bucket of work, which we're then going to do in order based on our own engineering abilities, and especially what is going to be driven by delivering more values to customers sooner. That might mean that we ship some C++14 features that are really high value that people are demanding, maybe before some C++11 features, but we will do them all. So let me lay out a roadmap as to what you can expect when. And the first thing to lay out is that there are 2 streams. And as we develop features and get them ready in the compiler, when they reach CTP quality, then they're going to be a candidate to go in the next CTP. When they reach release quality, they can be in the next version of Visual Studio. A CTP, just like you noticed in the CTP we shipped in November of last year, will often be a compiler-only release. It'll be on the command line compiler. IntelliSense won't crash, but it might give you red squiggles that are wrong, that kind of thing. And so that's a lower bar that lets you use the feature and we can get feedback on it. To actually release a product in Visual Studio, it also has to have IDE support, IntelliSense, debugger support, static analysis, and a higher quality level before we'll release that. So as each feature reaches those bars, it can be a candidate to go in the next scheduled CTP, the next scheduled RTM. And that first stream, RTM, depends on Visual Studio's cadence. And so as Visual Studio decides, we'll snap to that and we'll ship features as they become available in that. What we're going to spend most of our time talking about is the next 3 of these updates, the first of which you have in your hands today. The first is the Visual Studio 2013 preview, which you received 2 days ago, the RTM that's coming later this year, and that will be followed by another CTP, and I'll lay out what features we expect in each of those. A firm feature list for the first 2, and our best guess at the current rate and at the current date, and we will give you an update in the near future as to what we expect in the next CTP. So let's begin by talking about how that maps onto our promises. Because 8 months ago, at last build, I put up this slide, and I said we would continue to deliver C++11, which we are doing, and I'm going to share those updates with you now. But we also promised more batches, a CTP or an RTM, coming in the first half of 2013. Well, preview shipped a few days before the end of the first half, so that was good. But we promised batches, plural, and that's because we actually expected, when we told you this, we were trying to be as transparent as we could, and we expected we would be able to ship another CTP in the spring. When Visual Studio 2013 came together and we realized it was going to ship, and on this schedule, less than a year after we shipped VS 2012, that we're doing another significant major release, then we focused on making sure we had the features that were already ready for production quality, and we focused on putting them so that you have them in your hands today. I'll continue to be transparent, but we'll try to communicate better and set expectations and always keep you in touch, but we'd rather err on the side of more transparency than less. Let me lay out what's coming in preview. So as already announced earlier this week, in the preview build you have today, you have all of the C++11 language features that were in the November CTP. That's explicit conversion operators, rostering, literals, delegated constructors, function template default arguments, initializer lists, and variadic templates. But unlike the CTP, now you've got full IntelliSense for them, debugger support, and I'm happy to say a go live license where we will support you writing production code with these C++11 features with the preview release. So we're very glad to get that to you. But that's not quite all, because there's a few other small things in preview you might have noticed. One of them is that we added, of course, standard library support for those features. Where the standard library is specified to use those language features, now we don't have to fake variadics. We can actually use real variadics. And with variadics in particular, one thing that meant is you might notice that if you are compiling your projects that use STL headers, standard headers quite a bit, you might notice that your compiles are a bit faster and they use less memory. Because it turns out that real variadics are cheaper to compile than fake variadics. So by implementing this and using it in the standard library, we have some faster compiles and reduced memory for standard headers, which is a happy effect. In addition to that, we're also happy to show you that you'll get just a few, this isn't a big thing, but for completeness, you'll start to see a few C++14 features, and most of the features that I'm mentioning in this bucket were only approved 2 months ago into the draft standard. They are not in any official standard yet. They were just approved into the working draft in April, applied in the working draft that became public in May, that is now an international ballot, and that includes make unique, cbegin, cend, and a few other things. So you're starting to see a bit of C++14 in preview already. If you didn't notice it, you've already got it. So that is the conformance update for preview. So is that a good set? Are those features that you want to be able to use? Right, polite applause, because, well, you actually sort of gave us those features in the CTP, and we sort of were expecting them anyway. So, in particular, when we talk about the CTP and RTM stream, I want to be very clear. When something goes to RTM, we want it to be production quality. And there's also an expectation not to break anything. So you might have noticed on the slide where I talked about the RTM features, most of the time as conformance features become available and they're at RTM quality, they'll most often go into the next major release of Visual Studio, which used to be every 2 or 3 years, which is like a dog's age. But now, as you notice, it's been turned around in under a year since we shipped Visual Studio 2012. So expect that to be a faster cadence. At the same time, it's possible some of them might be in updates. Don't expect it, but if you happen to see some, it's a happy surprise. But we certainly will not put breaking library changes in updates. For example, to conform here, the tuple header for variadics was completely rewritten from scratch. There's no way we're going to shove that into an update. But now you'll have a faster cycle of RTMs as well as a series of CTPs. Now that's preview, but that's not actually everything that's in Visual C++ 2013, because RTM is coming later this year, and it's going to have some additional C++11 features in it. The first of those is non-static data member initializers. I know many of you have been asking for this feature. This is a poster child for how adding a feature to a language makes the language simpler. At first you think, oh, look, you added a feature to the language, and the C++ standard just grew by 2 pages. Obviously, it's not simpler. Well, hold on. There is inherent complexity in the problem domain, which is techno-speak for saying there's stuff you got to write anyway. And you can either write it by hand, or you can have language support for it. You are going to initialize, I hope, all of those data members in your class anyway. If you have initializers, you can do the common initialization in exactly one place instead of repeating it in every constructor, and hope you got it right, and hope the places where you put a different initial value are the ones you intended to have a different initial value. Very hard to code review. This is not just less code, but it is more robust code, and it leads to simpler code because we have this important feature in the language. So we're very glad to be able to have that in as part of the feature set for Visual C++ 2013 RTM. That's the first feature. The second feature is equals default. Sometimes you just don't want to bother writing the function that the compiler would write for you. Sometimes you have to write it because it would have been suppressed otherwise. In this example, because you wrote copying yourself, you don't get the default constructor. Well, now you can resurrect it without writing it yourself by simply saying equals default. And at first you might think that's a convenience feature. And it is, but it's more than just that. As summarized in those first 4 bullets, there are many reasons why you want this, but one of them is this can let you do things you could not otherwise do in C++ before this feature, including if you're writing a pod type or a trivial type, one that's bit copyable. You lose that as soon as you write your own default constructor or your own copying operations. Now you can preserve that podness by using equals default, as well as saving yourself some typing. A third feature that we're going to ship in Visual C++ 2013 RTM is equals delete. Equals default and equals delete are 2 different features, but they're often used together. For example, if you delete the copying operations to suppress copying for your type, as shown in this example, then you still want to resurrect the default constructor, which may do exactly what you wanted, and then you just say, oh, equals default. And that is much simpler code than the idiom in C++98, where you had to take those copying operations, make them private, not define them, which means you get a compile time error most of the time, except when it's a link time error. Here you can just say what you mean. Now, most people, when they think of equals delete, they stop with these special member functions. But it's actually useful for more than just those special member functions. It's also useful for eliminating overloads. For example, let's say you had a function bar that takes a long. If you only provided that first version, you could call it with an int and it would work. It would just widen it to a long. But let's say in this example you only wanted your function to be callable with something of the size and width of a long. Then what you do is you overload it to take a long and equals delete that overload. Now if you try to call it with a long, overload resolution will find the second one and say, doesn't exist. You get a nice, clean compile time error. You can express exactly what you mean. If you try to call it with an int, it will also fail. Slightly different reason. In this example, it would be ambiguous, but you still get the effect you want, which is I only take a long, and I can say so in my code. And just as a teaser where you might use this to overload on something interesting in C++11, R-value references, imagine that you were writing your own custom regex iterator, which unlike the standard one, is going to use equals delete, this equals delete trick. When you create an iterator over a regular expression, what you want to do is pass it a regular expression, and it's going to keep a pointer or a reference to that regular expression object. Everything's fine so far until you notice you could construct a regex iterator from a temporary regex, which works and stores a pointer to the thing that immediately gets destroyed, and everything's fine until you actually try to use the iterator, and you go off dangling pointer land. You can entirely eliminate that problem by overloading on R-value references, and if you write an overload that takes a const regex R-value reference and equals delete that, it is now impossible to construct a custom regex iterator from a temporary object. And this is how you can write safer, cleaner, more robust libraries. So we're very happy to have that as a third feature in Visual C++ RTM. And there's one more C++11 feature we're going to ship, and that's using aliases. There were no templated type defs in C++98. Instead, you use the hack around in the first line there, where I can't make a type def a template, but I can make a class a template, and I can stick a type def in a class. Problem solved. It's so easy. That's what we've been teaching people for 15 years. And yes, it works, but you have to say : type, which is kind of annoying. And it's even more annoying when you have to say type name followed by : type, as in the declaration of the template f. But the worst part is that when you do that, in a case like f in that third line, now that's a non-deducible context, which means if you just call f with some type, it can't deduce it, because it's like this weird nested type def thing. That's kind of icky, which means the caller of f has to instantiate not vector of int, but just int. He has to know the right thing to instantiate the template specifically with. This is what we call annoying. What we can do now is simply say using vec equals whatever and templatize that if we want to. The alias works without type name, without : type, and it's deducible. And basically it does what people thought always could be done, and were always surprised when it didn't work. And we're now glad we have that. The reason there's a little space at the bottom of the screen is because here's another example of where you're also going to get a small C++14 feature in Visual C++ 2013 RTM. Because 2 months ago, as part of the things approved in Bristol, was a really cool set of template aliases proposed by Walter Brown, Emeritus of Fermilab. So thank you very much, Walter. We're very glad of having that support. And it means that you can drop that type name and colon type from all of the type traits in the standard library and simply write something like make unsigned of T directly. No type name, no colon type. That was just approved as part of C++14, but it's in Visual C++ 2013 later this year. So that's the set of features that you can expect from C++11 and a little bit of 14 in Visual C++ 2013 RTM. That's what's coming next, hence the second column. Now let's take just a little digression, and for a couple of slides we'll talk about something that's not C++. Our customers want C++ conformance. We want C++ conformance. But customers ask for a lot of things, and in particular, one of the things that one group of customers really does need is conformance to another standard. And although we're not targeting conformance to any other language in our Visual C++ compiler than C++ at this time, and we've announced that and been clear about that, sometimes there's tactical low-hanging fruit that can unblock people. And so we've gone to our C compiler, which is Visual C++ when compiling a .c file or when compiling in C mode. There we've added the C99 features, variable declarations, the bool as a strong type keyword, and compound literals at the bottom of the screen. If you're not a C programmer and you haven't seen those before, they're similar in nature to, it's sort of a C version of initializer lists in C++11 with slightly different semantics. It's their own thing, and so they're only in the C compiler. And we've also added support for designated initializers in C, which is really useful for many people. Are those things that you would use? The reason I asked is because I started to hear a clap or two that were lonely, so I thought I'd say, okay, are there more of that? Because clearly most people expect Visual C++ to be a C++ compiler. That is our bread and butter, that is our focus, and we're working hard on that now. So why do these particular features? Well, because they unblock many popular community libraries. Just curious, how many of you have used or would like to use FFmpeg? I'm seeing a few hands through the audience. Well, that's great. It's a nice open source community library, which unfortunately doesn't compile in Visual C++ until version 2013. So we're very glad that FFmpeg and a few other important C libraries can be unblocked by adding these features to Visual C++ 2013, and that's the conformance feature set that you can expect later this year in RTM. Looking beyond this release, which now is has been on this one-year cycle, and so as we know more about future releases of RTMs, we'll communicate that. What else are we going to do? Well, I mentioned a CTP coming out. And so I wanted to give you an insight as to what we're working on. Now, this next set of features I'm going to show you, I am not saying that every single one of these is going to be in the next CTP. I expect many of them to be, but the key is on many, and that has a way of growing into all. But these are the things we're working on. We're trying to give you transparency because as we finish the work to deliver the RTM of VC++ 2013, we're already hard at work on several other conformance features. So here's an insight as to what the Visual C++ team back in Redmond is working on right now. And a subset of these will be available in the CTP that comes after 2013 ships. First, a couple of small ones, but they appear on conformance lists as papers that were voted in, and so we want to be complete. Under func, and the extended size of our features that are going to be that we're working on right now. And the under func is not the same as the one in C. So C++ and C did different things here. This is the C++ one that we implemented. And also size of basically just works in places where you thought it already did, but didn't before in C++ 98. And in particular, you can take the size of a member of a class without having a fake object of that class type. So those are features we're working on right now. Just a couple of small things to start. The next feature that we're currently implementing is implicit move generation. So sometimes this is called R value references v3 because we implemented move semantics before the standard was finished, and so we kept having to update it to track the way the standard went. And this completes that part of it because it's the implicit move generation that was adopted at the Batavia meeting just before C++11 shipped. And it means that in this example, we will implicitly generate member-wise copy and member-wise move, so that this code is just clean, clear, and efficient, doing move and no deep copying. So that's kind of nice. The one note I'll put in is that probably the first time you see this feature in a CTP, you'll be able to use it on every function that you expect except for move operations. And, sorry, that was by, when we first shipped def equals default in Visual C++ 2013, it'll work for everything except move operations. Because equals default says, give me the implicit one. Now that we're adding the implicit one, this will also light up the rest of the equals default feature so that equals default will do what the implicit move generation does when you ask for it explicitly. One thing that more is needed beyond this to complete move semantics support up to the C++11 standard. And that is the next thing we're working on, which is ref qualifiers for this. So just like you can say const and ref and R-value ref on parameters, so you can say it on the implicit this parameter, but you have to stick it at the end. That's where const and volatile always went on a member function. Well, ref and double ref go there too, and so we're implementing that, and that will complete the move semantics support in Visual C++ up to C++11 standards. But we're also working on some C++14 features. In particular, we said that there are some high-value C++14 features that we'll do before some other features in C++11 because we know people really need them, and they're just really convenient and useful. One of those is lambda return type deduction and function return type deduction. Let me cover those separately. They're similar, but I'll do lambdas, then functions. In C++11, you could write either of these lines, and they mean exactly the same thing, assuming some type is the type of the expression. But you don't have to spell out the type of the expression. We'll just deduce it for you. This is a cool, wonderful feature. Everybody loves it. And then they find out it only works if the body of the lambda is a single return statement. How many of you have enjoyed that? Right. So, and then you find that out, and then you say, oh, well, wouldn't it have kind of been nice if I could have written a longer function body with maybe multiple returns? And so the C++ committee knew about this, has been working on it for about a year, looking at the proposal, and in Bristol we approved 2 months ago for C++14 this automatic return type deduction for lambdas, where lambdas can be arbitrarily complex, have as many return statements as you like. As long as they all resolve to the same type, we'll deduce that for you. You do not have to say it. Now, most of the features I'm showing you in this section of the talk are things we're working on right now and that are probably going to be in this next CTP. I happen to know that this one is for sure going to be in the next CTP because we shipped it last year, you might have noticed. This is actually already implemented in Visual C++ 2012 from last year. Because we knew this change was coming in the standard. It had not even been approved yet, but we saw which way the core working group was leaning. It was a useful extension. So you might have already written this by accident, not knowing it wasn't standard yet. So you have been using a little bit of C++14 already in that case. But what's good for the lambda is good for the function. Why should lambdas get all this love when we still write functions as member functions, as function templates at namespace scope? And so in C++11, we have now 2 ways of writing the return type explicitly. That's in C++11. But in C++14, we now, as of 2 months ago, we have voted in and approved the extension that now you can do the same thing for function return type deduction as for lambdas, have arbitrarily complex internals of the function. As long as the return statements agree to the same type, we'll deduce them for you. Now, of course, this means you have to have the definition of the function. And you might say, oh, well, that's not good for separate compilation. And you're perfectly right. It turns out that a lot of our functions are in header files anyway because they're templates. So I suspect we're still going to, this is such a new feature, it was only approved into the draft hardly 2 months ago. So the community doesn't even know the right guidance to give. I do not know if Scott Myers, who may be watching us, maybe you can tell us, Scott, in the comments on this post, or on this video, are we going to tell people to prefer auto return types? Don't know yet. We're going to gain experience with the feature. But this is something we're working on that's going to round things out with lambdas and again makes C++ a simpler, cleaner language. Remember, when you say something twice, you might lie accidentally. This way you don't have to say the type twice, and you can deduce it and it stays correct under maintenance. And yes, these can be recursive. Don't ask. Yes, if there's at least one return before the recursive call, we can deduce it. Probably the second most requested feature from C++ 14 that people have been demanding, including our customers and C++ customers and other compilers, is generalized lambda capture. That name is important, and I'll explain why in a second. In C++ 11, we had lambdas which could capture by value, they could capture by reference, but what's the third thing that's obviously missing from that list? Move capture. You can capture value, reference, oh, but not our value reference. Well, maybe that doesn't hurt. Well, what if you have a move-only type, like a unique pointer? Turns out those are kind of popular these days. And you can't capture that directly in a lambda. So that first pool.run statement, the lambda has the two question marks. What do you write there? The answer is you don't, because there is no way to capture the unique pointer. You can't copy it. It ain't copyable. Yes, you could capture a reference to it, but that's not what you want. You want to move the ownership, and you cannot express that in C++ 11 with lambdas. Instead, this is the poster child example of why in C++ 11 sometimes you have to resort to std bind. And I refuse to explain that bind expression. I will only note, this is the workaround, it works. And for extremely subtle and non-obvious reasons, it's really, really, really important you put that ampersand in the middle. That's all I'll say about it. In C++ 14, in your capture list, you simply say equals move UPW, and you are done. So a lot of people say, oh, great, C++ 14 just got move capture. You approved that 2 months ago in Bristol. And that will get certain people, including Bjarne Strostrup, hopping mad, because he insists we should not call this move capture, because that's what everybody asked for, and the committee gave a superset of that, gave something much more general. It gave you move capture and a whole lot more. In fact, even in this example, if you look closely, notice we're capturing UPW by move, but UPW doesn't appear anywhere in the lambda body. If you look closely, you'll have noticed we also renamed it along the way. So then what on earth is W? Oh, W is simply a new local data member in the lambda object. In fact, you can declare arbitrary numbers of new local data members inside your lambda objects to capture state by value, initialize them with something, and use those stateful lambdas over and over again. You can rename references to outside variables that are in the local scope that you capture references to. All of that was just approved in C++ 14. Nobody knew at the beginning of the meeting whether this was going to go through, and I think at least a few people were happily surprised that it was approved. I'm certainly glad it was approved. Thank you very much to all the people who worked on that and the committee for working hard on this and many other features. We got it in the standard, and we are working on implementing that feature right now for Visual C++, and we hope that that will be ready in time for our next CTP. Anything I mention that we end up not getting all of it in the next CTP, you'll immediately know which features to expect next in whatever release vehicle. So we're giving you a roadmap so you can see the order in which we're doing things, and we'll be specific about dates more and more as we know more. We'll share that. But I said that was the number 2 most requested feature in all of C++ 14. What's the number 1 most requested C++ 14 feature? I know at least one person will say it. Generic lambdas. Some people have been asking for this for years, since there have been lambdas in the standard, because one of the things about lambdas that can be a little annoying sometimes is you have to spell out the parameter type, when in many other cases we can just deduce it. We're getting very used to this in C++ with auto type deduction, with template parameter type deduction. And now, as of the Bristol meeting 2 months ago, what we approved for C++ 14, draft 14, is we deduce that type. You can write auto, and we will deduce the type for you. But it's more than just deduction. It's more than just convenience. It actually gives you power, expressive power you do not have today. Because when you write auto on that function as a parameter, what actually gets generated is a template. Now, be very clear. It is not a templated class. That lambda closure is just a plain old class that gets compiler generated with some weird, unutterable name. It's still a class with some data members, the things you've captured. And it has that function call operator. It is the function call operator that is templated, which means I have a single object of a single type, and I can invoke it with arbitrary different types, can be different every time. And that gives you power we never had before in C++ 98 or C++ 11. And in particular, if you look at the last example of each section, the size example, we capture a lambda where in C++ 11 we say it takes an unordered map of W string and something and then returns its size. And we use automatic type deduction there. In the corresponding C++ 14 code, you can just simply say auto. Take by const auto ref, because auto you can always tack on a const or a ref if you want to. And we call dot size. And that will now work on not just an unordered map, but on any container that can report its size. And it's not just containers. It will work on anything that has a dot size member function on it. And what's better is because we reduce the return type, every time you call it with a different type, we stamp out a different instantiation of the template with exactly the right type that that particular size function returns. So you get deduction on the way in and on the way out with full fidelity. This is a great value add to complete C++ 11 lambdas. It was just voted in 2 months ago in the C++ 14 draft standard, and we're working hard to implement that, and we have high hopes that this will be in the CTP. We're pushing hard to make sure that this one gets into the next CTP that will come right after RTM. So in that third column, here are the things I talked about that we're working on today. Now, while we have several compiler developers working on these features, in parallel, we're also working on a few others. And so some of those two middle columns, some subset of that, don't know what yet, we'll tell you as soon as we know, some subset of those two middle columns are going to be in the post-RTM CTP, the next CTP that we ship you, of Visual C++. So we're very much looking forward to things like constexpr, user-defined literals, no except. And if we get no except or user-defined literals as soon as those are in, notice at the bottom of the column we'll also implement, of course, the C++ 14 extensions just approved 2 months ago that use them in the standard library. So when we have that, you'll be able to say, quote, hello, quote, little s, and that is not a const char star. That is a stood string literal. And other very useful literals in the standard library that were just approved 2 months ago. So those will light up in the library as soon as user-defined literals get into the language, some subset of those two columns in the next CTP. So now how close does that get us to full conformance? Because I said I would define what full conformance means to us. Well, certainly full conformance means implementing all C++ 11 extensions, library, and especially language extensions. And I believe this is the complete list of remaining C++ 11 new features in the language, and that this will bring us to a full implementation of all C++ 11 new features. They're mostly smaller things than the things on the left because we're doing them in an order where we're trying to deliver more value sooner. But some things take longer just because they require more engineering in our compiler. Our compiler is an older compiler. It's very robust and mature. It's never had ASTs, for example, like Clang and GCC have had. So as part of the re-engineering work we're doing internally is we're stripping and rebuilding the engine, parts of it, while we're on the racetrack, and adding ASTs to the compiler. And so that will enable things like constexpr and some of the other work to light up fully, including all of the things you see on the screen. Now, when you look at that, if you're keeping score and you say, yeah, those are all the C++ 11 features, it's at this point you might say, oh, well, looks like we ended the slide early with space left over because that's full C++ 11 conformance, isn't it? Implementing all the C++ 11 features? We don't think so, because that's not quite the same thing. The reason that implementing all of the new C++ 11 features isn't really full conformance to C++ 11 is because our compiler was only ever mostly conforming to C++ 98. It was largely conforming. The cases where it wasn't were largely things that you would not notice most of the time. But there were two in particular we need to go back and fix. And that as for full conformance to C++ 11, and that is the preprocessor and also two-phase lookup in templates. By the way, one of the reasons that we never could build two-phase lookup was that was really the one feature that for us required an AST, which we never had. We're now building that. That will enable us to finally conform to that feature. And the preprocessor basically comes down to that we didn't do the phases of translation exactly in the order mandated by the standard. So certain preprocessor techniques did not work. You may never have noticed this, but some people did, especially those building preprocessor-based libraries that tried to make them even more powerful. And so we will conform to that, as well as all of the C11 variadic macros that were voted into C++11. So I believe that this list is full conformance. Once we implement all of these things, that's the roadmap to full conformance to C++11. Now you'll notice the color coding. The black things are C++11 features, and the blue things are C++14 features, and there's quite a bit of blue here already. So if that's C++11, what remains to be fully conformant to C++14? Because C++14, it's not done yet. I mean, we just did the last check-in 2 months ago, and we're just now in balloting and testing for the next year. It's not an issued standard, but we know its feature set. So what is remaining to fully conform to C++14? 3 main features: generalized const expr, dynamic arrays, and variable templates. And I believe that that is a complete list of features which, when implemented in Visual C++, will make us a fully conforming, not just C++11 compiler, but C++14 compiler, and that's our target. So we're looking forward very much to gradually delivering more of this roadmap. And you'll notice that toward the left that we're doing first, there are more specific dates. Then in the middle, some of these in the CTP, and we haven't got dates on the last 2 columns. We'll definitely communicate more when we know more, and so expect to hear from us on that. You might notice that there are still 2 empty slots, because we don't think that conforming to C++14 is actually enough to do what I said at the beginning of the talk. Now, I phrased it pretty carefully. I think the words I used were, and you can scrub back in the video if you're watching this afterwards to see if I got it right, to aim to full conformance to ISO C++. I deliberately tried not to say just standard C++, meaning the main standard, because remember, we're actually decoupling work and delivering a wave of things in C++14. The main standard, of course, is the crown jewel, but we're also shipping a file system technical specification, a networking specification, which is a simple beginning of a networking library, and a concepts language technical specification for template constraints. One of the features that was punted from C++OX and is now coming back, and it looks like it will be ready for a technical specification next year. Our goal is not just to conform fully to C++14, but to conform fully and implement the entire C++14 wave, including those 3 features. And that means that we'll also intend to implement Concepts Light, that concepts technical specification, as soon as it is ready. And it's pretty far along. We expect it will be mostly feature complete at our next meeting or 2, and we look forward to implementing that along with the rest of the C++14 wave. And we think it's really exciting the energy that's going into C++, the rapid release cycles in the standard and in the industry, and that's something that we aim to be part of. So there is a roadmap of what to expect and roughly when, and we'll fill in more details the closer we get. But there's still one thing left to talk about. Because in that, going back to the 3rd column, in the out-of-band CTP we have planned for after 2013 ships, there's one more thing that was the #1 request for those of you who are doing WinRT programming for Windows, for tablets, for phone, using C++CX. The #1 request, and I alluded to it last year at Build, 8 months ago, on this same slide, when we said we promised we would continue to invest in platform support in C++CX to solve problems like asynchrony and continue making code easier to build in C++. And an example of both of those that I gave was await. I didn't say anything more, and you might have been wondering, is he serious? Is C++ really going to get await? And the answer is yes, we are. So one of the things that we are planning to put in the CTP later this year is an implementation of async await. And you'll notice I put this on the conformance roadmap because this is one of those longer pull features that are not yet part of the C++ standard or a draft of it. but are being actively considered for potential standardization. And the committee may decide to do it or not, but we have already for over a year been proposing the work, and we are now contributing an implementation of that work that people can try out and make sure works. And this is in the spirit of what C++ does. If you look at the major compiler vendors, this is not an exhaustive list. There's also others like EDG and others who are doing great work and have contributed to standardization for a long time. But if you look at GCC and Clang and Visual C++, all three have a history of innovating in features beyond the standard that their customers need and then contributing that work for consideration by the standards committee. And the committee does not take every feature offered to it. Good thing, because how big would it be? We'd have a huge language and all these different features. But it takes all these contributions and says, you know what? Yeah, we think we will take that one. And we think we'll take that one, but we'll modify it a little because we don't think you did the design of that part quite right. And then everybody's happy and conforms to what is voted into the standard. As you can imagine, if you're in a busy committee meeting and you get features coming in and somebody has a bright idea and writes a 3-page paper saying, here's my cool idea of a feature, it may not be all that technically sound. It may not be fully thought out. And so one of the things that really helps sometimes, especially with features that we don't have a lot of experience with, is when somebody actually goes and contributes real hard work to implement a feature in a real compiler in support of a standards proposal, so that at least we know it actually works and people can try it out and gain experience with it. That was done in GCC with variable templates that have just been voted in to C++14. Gabriel Dos-Reis did that. Andrew Sutton did the implementation in GCC for Concepts Lite in support of that technical specification that we're currently progressing. And it made a big difference to be able to try out an implementation, know it was implementable, know what the consequences of design decisions were. In Clang, we saw generalized const expr and generic lambdas, both of which now are part of draft C++14. And Doug Gregor is hard at work on modules, implementing modules for C++ in Clang as a prototype in support of a standards proposal. And we are now doing the same with async and await, so that we can get experience with the feature. And if the committee decides they would like to use the feature, with tweaks, we'll snap to whatever they decide. If they decide that they don't want the feature, that's fine, but it's always contributed and available. So let me show you why this is such an important feature. If you have ever used async and await in C#, or if you have ever done async programming, highly responsive, continuation-based programming, you probably don't need to be told why async and await are desperately important. For those of you who may not have had that exposure, let me give just a couple of examples. This is not going to be an entire talk-length talk on async and await. I may do that in the future. But let me just walk through a little bit of code to illustrate what the problems are that are being solved and why it's so important. In these examples, I'm going to use our PPL task of T. So the standard has future of T, and future of T has all the blocking waiting functions, such as .wait and .get, but it doesn't have the non-blocking ones, .then, when any, when all. Those are being proposed for the standard, but until standard future gets them, we're using task of T because it already has those non-blocking ones. And all of what I'm about to show you will also work on an extended future of T. So let's say you want to open two files, add their sizes together, and return the result. Well, this code does that, but it does it in a blocking way. It launches two async operations, open file 1, open file 2, concurrently then, when they're concurrently opening, when they're then ready, you will get the result of the size of one, get the result of the size of the other. But whoever is calling this code has to wait for this all to be done. The calls are internally concurrent, but there's no concurrency exposed to the caller, so the caller has to wait for all of this to finish. That's a blocking style. It blocks the caller. You don't have to do that already. In Visual Studio 2012, you already know that you can use .then continuations, and you can say, open file 1, open file 2. When F1 and F2 are both available, .then execute this piece of code. Now, the .then, the continuation is stuck on the end of the future, so to speak, right away, but we don't wait for it to finish. We just return. We just launch the two open files. We say, oh, by the way, when you're done, do this also, and we return. And that means we return a task of size T, not just a size T. And now the caller doesn't have to block. He can if he wants to, but he doesn't have to. This function can be used in highly responsive code that does not block. That's really important. Well, what does await let you do? The await feature is like a layer on top of .then, task.then, future.then. It is language support, which basically writes the code on the right for you, but way more efficiently than you can write by hand. And the way to think of it is you simply change all the .gets in the top left code, you change them to awaits in the bottom code. And the bottom left code is semantically the same as the right code, but you never had to write .then. You never had to write tuple, when all, any of those things. In fact, it's really powerful because if you compare the code at the top left and bottom left, you'll notice that they're structurally the same, and that is insanely important. Because if you have to resort to the .then style, it turns out that your code gets really hard, really impenetrable, really fast. Whereas if you can just write await, you can keep the same structure, but your code is non-blocking. You still return a task or a future instead of a value, but you have non-blocking code. By the way, as an aside, you'll notice that in the CTP, we are probably going to implement those with the keywords under async and under await. And that's because they're currently being actively considered for standardization. And as long as that's the case, we don't want to take those words that might interfere with any meanings that the committee might choose to tweak. And then we leave those words ready so that we can then implement whatever the committee decides and the semantics they decide on if they approve the feature. At this point, if you've never seen this feature before, you might still be underwhelmed, saying, well, you know, I'm a C++ developer. I'm not afraid of no.then, and I'm kind of liking lambdas now anyway. The more the merrier. That code on the right isn't that hard. It just proves I'm a good programmer. It gives me a chance to be an alpha geek. Yeah, if you think you're an alpha geek, now try this. Just try anything with an if or a while loop, and we will all sit at the side and watch you and read our email while you struggle with it. Let's say you try to read from a string file name, and what you're trying to do is asynchronously open the file, then do async reads of each chunk of data in the file, and append a suffix to it. Let's do a straw man example. This code does that, but it's blocking code. It says open file, but immediately says .get, which blocks. It waits. Then it creates local variables. Oh, local variables, how easy are those? Ret and chunk. And then we go through a little loop where we call read, which is an async call. So again, we immediately block. And we get the size. If it's not empty, we record it and its suffix. And we keep going, doing async reads, blocking each time, until we get to the end. We get an empty chunk, and we're done. So let's now rewrite this with .then. You probably noticed the pattern already. Whenever you see open file and then you see .get, what you change is you change .get to .then. So let's do that. So we return open file, okay, .then. So whenever the file is open, .then, I've got an iStream back. Then, okay, I have my local variable string ret and chunk. Now I'm going to have my while loop, and I'm going to call the async read. But now notice with the async read, the very first thing I then call is .get, which means I translate that to .then. Okay, so I call fi.read .then open paren. What comes next? How do I now, but I'm in a loop. How do I say now go to the beginning of the loop again? I can't do that because I'm not lexically in the same piece of code. I want to sort of execute the rest of this loop iteration and the first part of the next loop iteration, which aren't lexically contiguous. And it turns out that there are solutions to this problem. I usually don't show code that I don't know if it works, but I don't care, because you should never write this. I have no idea if that code even compiles. I didn't bother to try. But it shows you the kind of thing you would need to do. The first thing you need to do is you have to say, well, wait a minute, each time I call .then on the read the next chunk, I'm going to have to invoke a lambda. That means my local variables can't be local variables anymore. They need to be on the heap, which means reaching for make shared or something similar, and copying shared pointers to them. You could combine them and save an allocation, but it's not worth it. So there's so many other problems with this that's the least of your troubles. So I make shared string. That's going to be my ret. And then I'm going to make shared, now notice this is where it gets really fun. I'm going to make shared function of task of string. Why? Because I'm going to have to make a lambda and give it a name and put it on the heap. Because I want to make a lambda for the dot then, the loop continuation, but I have to call it multiple times from within itself, which means it needs a name, which I have to be able to capture. So notice that the lambda actually captures its own name, dot, which is next, that local variable, and it takes a shared pointer to itself. Yeah, it's getting real fun now. And so once you've got your function on the heap, it's ready to recurse and call itself again when it needs to with the charming paren star next paren semicolon call. And then once you've got all that ready, you haven't done anything yet because all you did was create a lambda. And then as your last thing to get the whole thing rolling, you call return star next paren, which calls the first invocation, and then it calls itself recursively until it's done. I have no idea if that compiles, and I don't care because I want to write await. I want to write the same code as in the top left, and bless its heart, all I did was change .get to await, and this is so much easier to reason about. This is important for us to do because it is, like I said, it is the #1 problem with using C++ CX to write WinRT apps today. Because if you have portable C++ code that runs fine on another platform but is blocking, now it's true, if you want to bring that to WinRT, you're forced to make it non-blocking because WinRT hates blocking. And it basically makes it very hard for you to block, which is a good thing. It's good for you, but still painful because without await, it means you have to take your code and turn it inside out and do major rewrite just to bring it to a responsive platform. Now, yes, you could say, oh, but it's good for you. You could say, oh, yeah, but you'd have to do that to make it responsive at all, so you have to do that work anyway. But it's still a real barrier to bringing code to make it responsive. And it's not just about moving platforms. It's about making code on any platform. And that's why we're proposing it for standardization, for Clang to be able to do this, for GCC to be able to do this, code on any platform to be able to be responsive and maintain the structure of the code. Here I can have my local variables, but remember under the covers, the compiler generates it into not what you see on the right, but semantically the same thing, modulo bugs, and does it right, and does it way more efficiently than you could by having extra stacks and just maintaining small stacks for you automatically, and you don't have to worry about those details. You can just write local variables, which will last as long as they need to, and write your code exactly as before, but change .get to await. And that is a real step forward. And yes, I've been talking about C++ CX, so here's your one C++ CX slide to show it will work also with WinRT, ref class on the stack. You can avoid having to ref new a data reader and then have to explicitly delete it to get it to let go. You can just write your code as usual, but make it non-blocking by using await instead of .get. And this is a big step forward. So we're very happy to lay out a conformance roadmap, not just for C++ 11, not just for C++ 14, but for the whole C++ 14 wave, and also be contributing a little something to future standardization that we hope may be part of a future C++ technical specification, maybe even part of the C++ 17 standard. That decision is up to the standards committee, but we want to do our part to enable our developers on our platform for you to do your work well and write responsive apps easily in C++, in Visual C++, and contribute that to the world if they want to use it too. So that's our conformance roadmap. We told you we would tell you what we knew when we knew it. And so today was a major update and the first time that we gave you an end-to-end roadmap to full conformance. We didn't give you specific dates. As we went further to the right, there were fewer dates because we don't know them yet. But as soon as we know, we will tell you. In fact, the next roadmap update is coming up in just over 2 months. Because if you enjoyed going to the Going Native conference that Microsoft held and hosted last year, which was 2 days of nothing but cross-platform ISO C++, which talks about Clang, talks about standardization, Well, we're going to do it again, and so I'm happy to announce today that registration is live now for Going Native 2013, which will be held September 4 to 6, just a little more than 2 months from now, in that same location. And our intent is to webcast that and to make it available, but there are going to be things you cannot do unless you're in the room. You will have interaction with the speakers. You will be there and have a wonderful C++ festive environment that we enjoyed. When in the middle of the conference last year, I was going to dinner with Bjarne Stroustrup and several of us and a few of the attendees together. Yes, dinner with Bjarne. And so we were going out, and Bjarne was just really enthusiastic. He said, "This is the most fun I've had at a C++ conference in years." That's what you can expect again. Bjarne is once again headlining the conference with the opening keynote. Like last year, we have returning Andrei Alexandrescu of Facebook, Chandler Carruth of Google, who's a lead developer of the Clang compiler and will no doubt give us great new Clang news that we're very excited about. We're excited about that compiler also. Stefan Lavave at Microsoft, and some speakers that we didn't have last year, including Scott Myers will be there to give a talk about C++ 11 and C++ 14. Sean Parent of Adobe, a longtime standards participant. Michael Wong of IBM, who casts Canada's vote in the standards process, and more. And we've expanded it to 3 days. Now, those first 2 days are it is a Microsoft-hosted conference, but it is about ISO C++ on all platforms. But when we did that last year, people were super confused. Like, people came and they said, "Why is there a talk about Clang?" Well, because it's good and it's exciting, you should know about it. But why is there a talk about Clang at Microsoft? Because it's good and it's exciting and you should know about it. But the feedback we did get is people were actually surprised there wasn't at least some Microsoft-specific content. So what we're going to try this year is adding a third day, and that third day is going to be a mix of cross-platform and Visual C++ specific content. That will be available for day 3. So 2 days of ISO C++ on all platforms, and a day that also includes Visual C++. And that's our intent. Register today because space is limited, and as soon as the summer months come over, we come back from vacation, meet us live in Redmond, and we'll have a great time at Going Native 2013. And I also will have a talk there where I will give you an update on this conformance roadmap so that as we know more, by then we should know a bit more about more specific things that are in those middle 2 buckets that will be in the next CTP, and I hope to have more specific news to share with you then. We'll tell you as soon as we know. Register today. Thank you for coming this week. Thank you for coming to this talk. I hope you enjoyed what you've heard. We're excited about the progress that C++ is making across the industry, and we're excited to be able to deliver you tools to use standard C++ for your Windows and WinRT applications. So thank you for coming. Enjoy the rest of the conference.